um, I thank you. Just now my camera is something saying, but I hope it gets back and you can see it. Very happy to be with you to share our work. Thank you for the invitation. Thank you for your time and your interest in our work. This picture comes from the times we could travel. 2017, I spent a very nice weeks in Korea, and this picture was taken by me in Seoul, but I had also very good feelings back to the time in Daejeon. We had good cooperation with people interested in inertial navigation with atom interferometers. At that time, we had been not a lot thinking about these possibilities, about other things mainly, but it was very inspiring, and we have been continuing working actually there. So you see, in a certain way, this cooperation is influencing us till today. So yes, indeed, I will speak about ground and space uniformity with both Einstein condensates. And when I got the invitation, I noted that you have a special interest also in dark matter and dark energy. And so somehow I'm not an expert in those fields, but I try somehow to bring up why atom interferometers, how I understand atom interferometers could be interesting for these questions. And this picture here shows the sky above Sweden combined with BECs floating there, because actually in one of our activities we have been demonstrating the possibility to create both ion condensates in space and to experiment with it. And I will only briefly report about it. I have a selection what I think is maybe most interesting to you. I would like to acknowledge funding from the large German Space Agency, very generous since many years. I'm happy that this has been substantiating also in two DLA institutes, one in Ulm, QT, and SI in Hanover. And we also have support from NASA. We are very happy to cooperate with NASA and US scientists, and also with our local excellence cluster Quantum Frontiers. So all this together and all our cooperations creates a unique research environment. I want to thank all, especially also all the teams I have been listing here on my talk. Names I think would be now more than 50, and so I think it's not time. So my outline is, I think the audience is quite general. I first talk about applications of light pulse interferometry with BECs, and I gave the statement from gravity to gravitation. And this somehow maybe also tells a little bit from where we actually come, or what is our main motivation. And this should motivate why that I explain a little bit about light pulse interferometry with BECs and why we want to use BECs, and finally about inertial sensing. And this means applications in detailed gravimetry on ground, in free fall, and in space. Yeah, so this brings me to my first slide, applications of light pulse interferometry. So light pulse interferometry is a statement about a special form of atom interferometry where we use light pulses to manipulate the atoms. And I will detail it later. And actually, this is a field of growing interest. Again, growing interest because the field already started out in the 90s, but it was interest driven due to the progress in atom sources. So the applications are Earth observation, of course, exploration, looking for resources, and navigation. thinks that this can be helpful indeed. Of course, in Earth observation, it is, and I made it bold because this is what I will talk today, precision gravimetry, also rotation acceleration sensing in general, and these observations for geodesy, geophysics, here especially hydrology, and generally you want to have reference systems or even earthquake warning systems. So there's a lot of somehow ideas around where you would like to have the benefits of light path interferometry. And of course, we came from physics, and there's a lot of interest in applying light path interferometry in physics. One is that since many years we study the possibility to get a more stringent test, a quantum test with atoms of the equivalence principle. And this has many limitations, but different ones to the classical. And we think that we can make at least stringent tests as has been done so far. And I think what is also a part of your audience of an interest, dark matter and energy, there has been already experiments. Then the general question is, you can, and I will not talk too much about it, but you maybe have seen in the publications. The question is about, I mean, when I have an atom interferometer, how far can I actually split apart these atoms? Are there any fundamental reasons that I don't observe spatial coherence anymore? And this is about how microscopic can I realize quantum systems. This large splitting is also one of the important levels of sensitivity that the atom interferometers may be of interest for gravitational wave detection in the infrasound domain. And of course, an atom interferometer itself, you have been maybe also following some of the literature, is an interesting system to study general relativity in a quantum system, because you know, in a classical thinking, a clock is a clear and a distance is a clear definition, and what a force measurement is and what a time measurement is, all is fine defined, very well defined. But now in an atom interferometer, you make a force measurement with phase. You have, you in principle can consider those as a kind of clocks, and so you see immediately that this is actually itself an interesting system. And finally, of course, atom interferometers more or less are applied for measuring or defining the gravitational constant, which is one of the least known constants, or also the h over m constant, Planck over mass of the electron, and this you can refer from the photon recoil in atom interferometers. So you see, there's a widespread. Today, I will mainly concentrate on precision gravimetry and the connections, why this may be interesting, and probably you can tell me more about it for dark matter energy. So I hope with this introduction, I have given you a motivation to follow my talk, and also to explain you a little bit what light pulse interferometry actually is. And before starting into exactly this explanation, I want to make a slight differentiation between gravity and gravitation, because I have been saying, yeah, geologists are interesting, but actually I want to point out that there are two somehow objectives. One, gravity means actually what is the fall acceleration, and when you more or less when you pull down to Earth as an object and you want to jump out of a plane, then this is something about gravity. And when you ask about is Earth really following the gravitational laws of physics, then we speak more about gravitation. And gravitation can be modified, for example, by new forces. And so in this statement, you already understand that somehow gravitation has a very applied side, which is gravity. And I just wanted to show you this here in this slide, because in school you learn about gravity, that gravity is has a constant. You know the first digits maybe, and then about something 9 meters per second squared, roughly 10, even if you want to be less precise. But actually gravity is continuously changing, because gravity is caused by the mass distribution, and the mass distribution of the Earth is changing. So gravity can give you information about how mass is floating around in our Earth, on our Earth, beneath our Earth, in the atmosphere. And this slide just shows you what all for signals geologists are interested in. And the signal can have a wide time variation. We have even now phenomena from the times where the ice ages, where the ice, the weight of the ice was compressing Earth, and it disappeared, and Earth is still rebounding from it. This is an extremely slow process. And others maybe are too fast for us, like ice melting due to climate warming. And then there are some others which are just intraday modulations, for example, due to the motion of the moon around the Earth. It's pulling Earth. And then, of course, you have also all the annual cycles, spring, autumn, rain, and you see, of course, if water is accumulating beneath you, then of course this is giving you an additional pull. And so gravity is a resource of information about what's happening on the Earth, above the Earth, and beneath the Earth, and is also exploited to get information. And how do we get this signals? And not just by throwing an apple, but we have currently spaceborne satellite missions, and actually in the satellites carrying sensitive accelerometers, which just feel gravity and maybe the drag of the atmosphere, but this you can correct for. But the trajectory is defined by the Earth's gravitational field, and this is not just a sphere, it's not a plated sphere, a ellipsoid, it's something actually much more less uniform than what you maybe have in mind. And actually the trajectory of this test masses or proof masses tell you something about actual gravity and how this changing. And while satellites, of course, orbit around the Earth and have limited spectral resolution, the other way extreme is that you really locally sample with stationary gravimeters or with gravimeters on boats or on planes. And actually, when you think about stationary gravimeters, again, I just want to say that we have a global network of gravimeters, and they are not only used for Earth observation on monitoring gravity and the vibrations and oscillations of the Earth, but also about possible search for dark matter. And so this is the first connection. And this brings me to the slide that there are several ways how such instruments can be used. On currently gravimeters are used. This is that actually you look for additional forces. Of course, you could also dark matter detect via the gravitational forces, but here, it's generally today, people are interested in that there are unknown couplings due to light particles that create non-gravitational forces, but you can detect them with instruments which can measure forces, superconducting gravimeters or accelerometers, to say, and also light particles barometers. And similar, also due to dark energy, so-called chameleon field, you can create non-gravitational forces, which you actually measure more closer to objects, let's say gravity on short distances, because it can easily mask, the effect can be easily masked, and it's somehow also again at the basic, at the end, the fourth measurement necessary. And again, somehow this is then in principle possible, this light pulse atom interferometer. So this lab was just to somehow sort a little bit out the connection, which might be interesting, which might already known to you, and which should somehow catch your attention. So how is light pulse interferometry working? Actually, it's a very, in principle, very simple. You let an atomic cloud fall. Man has been using first, atomic beams. They have a large speed, but nowadays, of course, we have made progress in cooling. So you have been widely used and now laser-cooled atoms. And laser-cooled atoms you simply drop or you launch them in a fountain, and then what you realize is actually that you shine tuned, but still close to resonance light, such that the atoms absorb photons and can also again emit photons. So I use my pen. I hope it's working. The idea is that here you have two frequencies of light shining in. You have your falling atoms. We use both Ernst condensates. I know why we process more complicated ways than just laser cooling. And in principle, you have one direction of lasers moving downward, but due to a reference mirror, and this is somehow, we measure the motion with this device, this is a reference mirror, it is reflected, and actually it has now the opposite momentum. Now the atom first gets excited with one laser beam in one state, and then precisely is stimulated equally by the opposite laser. And so because it's opposite and it's stimulated, you add actually, somehow you change to a new system, but you add recoil. So you start here out with a initial momentum, and here you have a final momentum, which is just plus 2 h per k, and this is the photon recoil associated with one of these laser beams. So in this way, you have to understand the picture on the right, that you have here, suddenly after applying the first laser pulse, a splitting, a coherent actually splitting of the atomic wave packet, or associated to each of the atoms. And in the same way as you can split those, you can actually transfer momentum such that they again move together, which you see here in this situation. They are more or less just oppositely bent. And at the end, they, at a certain stage, recombine. And if you apply here in the right moment, symmetric, you see here always the same time distance, then actually you create a similar situation as at the beginning, but for each trajectory coming in. So you actually get here an interference of two different paths, and in this way, and this path gives you intuitively information about the two different trajectories, the phase, and these two different trajectories are, for example, at two different aids. So this is how you see one has to climb against gravity more as the other. And if you study the phase, then you find it here below. So here, the phase is depending on the photon recoil, and c is then to gravity, but you can just generate it to any acceleration you want to measure. And c squared is, as you see in the right schematic, the free fall time the atom spent in the interferometer. So 2t is the complete free fall time, and so big T is defined by half of the free fall time in the interferometer. So what is important to understand is that first, this is a space-time diagram. This space-time diagram means that actually you see some. So you have to think it as on the left side, if you think about how will the setup look like in principle. And for those people who are not familiar with atom light interactions and Rabi cycles, because you can also understand as a Rabi cycle or fractions of a Rabi cycle. There is a very nice intuitive picture, because these two counter-refracting light waves, you can understand, are interfering and create a standing interfering pattern. And this interference pattern is actually giving rise to atomic diffraction. And then, according to diffractions, you get again the same results for the momentum here, which you see here. This momentum, you have more or less the undiffracted and diffracted atomic wave. So you see, you can have different pictures, and I hope one of these pictures is convenient for you. Very important is this formula here, because it tells you several. It tells you first that from the phase of the atom difframeter, you can measure the acceleration, or at least you get a signal from an acceleration. It is proportional to the transferred momentum. So if you would make a wider splitting, then you would get even more sensitive to this acceleration. And the answer is, if you wait, if the atoms for longer time in the difframeter, then you get more sensitive. It's simply because actually this measurement would be a differential distance measurement. Of course, if always a continuously accelerated system, the distance is growing quadratically. So, but this means that it is very useful to extend the time of free fall in the difframeter. Of course, in reverse, if you extend the measurement time, you are slower in reacting. So it's only in this way, if you choose this pathway, you are more sensitive, can operate at lower signal frequencies, because you need this wait time of the free fall. And now how it's practically measured is that actually in the measurement, you null the signal in a way that as the atoms are accelerated in fall in gravity, for example, you measure this with respect to your diffraction gratings. So if you let your diffraction gratings also fall, then more or less you should null the signal, because then everything is in free fall. You know, it's like the equivalence principle of Einstein. You should not note it. And in that sense, what actually people do is that they accelerate the lattice made of light, and if they exactly accelerated like gravity or the force acts, that they can null the signal, and then you know precisely from your chirp frequency, from your chirp of your frequency of the light, what the acceleration is. And this is what people mainly do. In this way, you can now measure gravity, and when you measure gravity with such an atom difframeter like we do in our in a simple tabletop experiment, and you see you can integrate quite long with such a device, and actually commercial devices would not work in our lab environment because it's too noisy. Normally I show a picture of our lab. It's actually an old castle. So once you come, you can see an old castle. And there in the third floor is standing our parameter to measure gravity. And then you see, if you integrate well enough, then you see, hey, there are problems occurring. So suddenly you get here a deviation from, it's not so stable anymore. And actually it's not your instrument which is not so stable. It's actually gravity, it's the Earth. Because what you see here is actually this variation, it's the tides. And at a certain way you say, okay, this is just how sun and moon pulls the water. And the tides is a very important information for the geologists, and of course all the other signals I have been mentioned. So you're not surprised that the couple of companies actually doing precise gravimeters and accurate gravimeters when differentiate between relative and absolute gravimeters. Absolute gravimetry is actually there are very few real devices, just actually only one. While relative gravimeters, there are many. What is a relative gravimeter? Now, a relative gravimeter means you refer to a certain quantity and you look to the temporal variations. But it's not so important now if you know precisely the amplitude of this variation. You are more looking into the variation. So they are relatives. So they are referred to another quantity which can drift in time. But when you speak about an absolute or an accurate gravity measurement, it means that you want to know precisely what is your acceleration, and you want to know it maybe 10 years later. And then you see immediately this is a difference. And actually, there is one device, I'm not talking more about it, which is doing the job in accurate parameters. This is a falling laser cube, laser interferometers with a falling mirror, which is then always put up again and you let it fall again, and you measure how this mirror is accelerated with a laser interferometer. Now, already from this explanation, you can understand that having just a ball of gas of atoms created in a fraction of a second, let it fall, and you make these measurements, is much less invasive than if you would have a falling macroscopic body. And you also need no mechanics. So you see already from there that actually atoms are a great resource for doing such an instrument. Nevertheless, also atom interferometers suffer from certain biases. And I just want to show you two examples where actually the atomic source is important. So the source features of your atomic ensemble. And one is on the left picture. Here you see actually in blue the atomic cloud in free falling interferometer. And of course, if you have a finite temperature, it's expanding. And now the situation is that you always have imperfections of your laser beam. And even if you would take the most pure mode, which is a Gaussian shaped laser beam, then you have a convolution of the motion of the atoms with your wavefront, which is normally a parabolic. So you have always this convolution. And this gives you, and combined with imperfections, this gives you a bias. So, and the other effect is that if you have a laser-cooled source of atoms, since this cloud is actually a laser cooling stochastic process, so you have a lot of fluctuations on it. And now, another effect is if you have not a precise zero velocity of your atoms, then due to the velocity and rotation of the Earth, you get a Sagnac effect, a Sagnac phase. You can also see it again as an acceleration and the Sagnac effect in a similar way as others, and so you will be sensitive. And actually, these effects are important as the limiting effects. So this slide should tell you actually that the motion of the atoms is a critical parameter to advance in light pulse gravimetry. And I just want to show here, I have brought with me the data of two of the state-of-the-art atom gravimeters, the GAIN, which is made in Colloquium in Berlin, and the cold atom gravimeter from our colleagues in CERT. And all the purpose is that you see that what I just presented you, the wavefront distortions, and they call it Coriolis effect, but actually for physicists, it's hard, it's the Sagnac effect, because Coriolis is a little bit different stories, you know. You have, again, quite a large effect. So actually, in a nutshell, the motion of the atoms is a decisive parameter. Expansion-like center of wave-back motion is a decisive parameter for many respects to improve atom interferometers. Maybe it's not so surprising for you, but for many people have been have been always saying, no, this is not so bad. But of course it is, and maybe it's somehow similar as if you look for the arguments, it's like if you need nobody to convince that a laser interferometer is maybe outperforming a light bulb interferometer. So in that sense, this is my introduction, Bose-Einstein condensates as a source for interferometry. Why do we do this effort? And Bose-Einstein condensates had never been considering as a source, because why? You have a lot of loss in flux when you use those, because to generate this state, you need evaporative cooling so far in most cases, and this is connected with big atom loss. However, if you have bias terms, you're not interested to know as with high precision what your atom number, your bias terms, if the bias terms drift and are not controllable. So maybe it's better to have a better controlled systems and less atoms. And actually, most people at the end filter the atoms that even when they start out with 10 to the 9, they work maybe with 10 to the 6 or 10 to the 5 because of filtering, like, for example, Raman filtering. So actually, there was a big progress in generating both angle states, and we have somehow also contributed with our methods. But I just want to recall one was that reason was that we wanted to have a well-defined motion, and so the BC actually can be very well tracked and can be very precisely released on micrometer positioning and micrometer per second velocities and also expansion velocities. And this is something which is a strong asset. It's a gain of order of magnitude with respect to other techniques. And the BEC somehow reflects your trap, and actually and can have more or less a perfect mode quality, means controlled spatial expansion, not a stochastic process. And moreover, this mode is not only controlled, but it's somehow from our atom optics like a point source. So I will show you pictures where you see the contrast between a BEC and a laser cooled system to understand that this is really a point source. And there are methods to more or less with a point source. You can really, you have methods at hand to lower the expansion rate. And we have a record in lowering the expansion rate. If you compare it to effective temperatures, we now speak about something like couple of tens of picokelvin, 38 picokelvin in 3 dimensions. I think you really can observe longer BEC with so small expansion rate. And this has a lot of nice connections because this method is based on that you let expand the BEC first, and this lowers your mean field energy. And actually you can control the size and the mean field also to a certain extent with this method. So you have a quite interesting control parameter to analyze those. And due to this extremely low expansion that you can achieve, you get, of course, a high spatial coherence, a high contrast, and a high efficiency beam splitting, because the light pulses are always scaling the energy with the photon recoils. And photon recoil energy is already quite low. And somehow, if you combine these and think about also squeezing, and you want to have then lossless beam splitters, because otherwise you waste all your squeezing efforts, then you understand why this source is actually C1 interesting for also entangling atoms. And so in this sense, I want just to motivate why we have been doing all these efforts. And this brings me to that actually today it's really amazing when you remember the times lab filling devices have been realized for creating BECs. Now with a lot of great ideas by Hans, Reich, Schmidt, many people who have been involved also from the US and many other places. We have been coming to atom chip sources where we are very robust, quickly can create both Einstein condensates, which we can use for metrology. And I just wanted to mention that these devices have also decent flux. We can now create about 100,000 atoms in a BEC or even more in something like a second. And this is somehow coming close to this, what you can actually, what people use by filtering Raman filtering with laser cooled sources, but they have only this in one dimension. And they could not, they would get much less atoms to do it in 3 dimensions. And moreover, this high flux BEC source is not in a laboratory, it is a mobile device. You can be transported around Germany. And I just show you here, this is an old slide, there are probably data to add, but this is what you see here, mentioned on this side. This box is meaning Quantus 2 is our second generation device of a mobile BEC interferometer and creating the largest fluxes. And I think it's still one. It's now a couple of years old. The paper is, I think, 2015. Yeah, so you see so maybe some changes in that time. But generally, I think it should be conveyed a message that now you have for laser pointer, and you have for an atom laser now atom chips. I mean, somehow this is very bold statement, but in a certain way it should give you the spirit. These things are now getting interesting for metrology because they are reliable. And just to visualize what I mean with the point source, here you see, it's already quite also slide, an experimental sequence time of creating 200,000 atoms in a BEC. You see that actually our atom chip has several layers and intervening a lot of different traps, which you switch between. But in order to understand what I mean is time of flight measurements, just meaning you release the atom and let expand it. You can see how fast they, with time of flight, how fast they expand. And now I can show you, I mean, I don't start with a thermal cloud of atoms in a gas because this would be microseconds. But here I have a time of flight chosen, 2 milliseconds. And each of these graphs. And for the BEC, I have been very unfair. I have been even taking a longer flight of times, 20 milliseconds. And now I show how the cloud expanded. And here you see a chip mod, laser cooled atom cloud expanding. And then you see this if you say, laser cooling a magneto-optical trap is not so bad. Oh yeah, you can then do molasses. Then you see this. And then you can say, okay, I can magnetically trap and evaporate. Then you get here always, you see actually now the shape of the atom chip magnetic trap. But when you're really down, then you more or less have this system. And in a certain way, this shows you what I mean with point source. And this is the reason why we can create so low effective temperatures, so slow expansion. And it's of course important because in space, you don't go for in space just because you want to do half a second or 10 milliseconds. At the end, you would like to do interferometry over 10 seconds. People dream of 100 seconds or 30 seconds in this, the atoms fall in the interferometer. And so just to understand how powerful this progress actually is. And here you see parameter. This is still shown at 330 nanokelvin. I speak now about pickle, but I show you also some pictures about this. And now, because this is so handy devices, atom chips, we have been creating a BEC in a transportable device. Yes, you are my student, Nina Heine. She actually more or less squeezed this with her team together, and she's not as large as I am, in this tiny device where you have here the atom chip. And actually, this is not the end of the miniaturization, but it's not what you are interested in anyway, applications. But it just show you nevertheless. And here you have more or less a system. You create this BEC on this tiny atom chip, and you let fall the atoms. And here you see your reference mirror I have been showing you. So you can directly match this simple ideas I have been starting to this experiment. And this multi-layer atom chip is for us the important quantity. And the very funny thing is, just for technical reasons or for principle, that the smallest part of this device is actually the atom chip. So this is why we are now working in miniaturizing everything else, because actually we think that in a shoebox you can do everything. Create a BC interferometer in a shoebox. Now this device is actually starting working. This has been the design has been and the starting has been done during the years. And I just show you here again our mod performance and then what we create in the BEC. We have now better numbers in the BEC, a little bit of higher flux, but for us this is sufficient. These are technical details. I don't want to buzz it with you. And here you see again delta kick collimation. So the way the BC is more or less the expansion velocity is nearly flattened out. Still, these are temperatures of a couple of hundred nanokelvin, and you see this is something much nicer than what you can do with laser cooling, but not the record I show you later. But for this device, it's already great to improve on systematic biases in future. I mentioned that we perform, mentioned the free fall time. Here we varied the free fall time. I said the sensitivity is changing when you increase the free fall time in the interferometer. This means actually that you are more also sensitive to the sweep rate of the laser. And here you see the sweep rate of the laser of the lattice. And depending on the free fall time, you get narrower and narrower fringes. Now, when you actually want to say, okay, yeah, I see always this fringe pattern, but how do I know that precisely at this value gravity is? So what you do is you actually choose different free fall times, and then you get different fringe spacings, but only at the point where the signal is canceled exactly, the sweep rate cancels the acceleration, it's always the same. And in this way, you pin down with more coarse measurements than when you do the fine measurement where you have a quick oscillation. And this is exactly what we're doing here. And we extend here, we have been actually operating in this area, and we have just now modifying the device to have to start to have the free fall down here. And in order, and this is why we also have been introducing the lens to have a compact object. And now from our estimates, from the gain of lowering the expansion rates, we think that we have interesting, we expect that we have getting actually interesting lowering biases. And but there are, of course, new effects, which are below here. And this, for example, came up recently in the last years, the black body radiation. But also this we estimate quite low. And of course, in BEC, you always have to think about atomic interaction. But there we think that we have, with some analysis tools, also a handle on to even improve below this value. Now, why I'm saying this is just because compared to the others, this here, this would be wonderful and would give you a complete new information about your environment, because this is telling you something about hydrology, because hydrology is starting at quite low in the microgal, and so you would have here a very precise and accurate instrument. And why is this interesting? I have been connecting at the beginning of my talk, saying we have gravity and gravitation. And gravitation is about the anomalous forces may add to gravitation. And of course, when we improve our sensitivity in gravimeters, this means also that we are approaching and even superseding maybe more and more super conducting gravimeters in a certain way. And this is why it may be also interesting for dark matter and dark energy research. And yeah, this brings me to the next step, actually, to the inertial sensing and gravimetry. And I mentioned that with our gravimeter, we think we can go below the microgal, but the people will say superconducting are even better, at least relative. They need, of course, accurate gravimeter side to be sure where you start from. But how to extend the free fall? Because this is our biggest lever. And we have actually a couple of fascinating environments to extend the free fall. One is that we have been creating, following Markasovich, but going beyond, a very long baseline atom interferometer I will briefly present. We have nowadays in Hanover an Einstein elevator, which is actually an elevator, as you know, but he is a little bit not so nice like a standard elevator, because in a certain moment, he just disconnects from you and you float in free fall. And but he's then again nice because before you smash on ground, he's approaching you and slowly deaccelerating you so that you will not hit too hard the ground. So, and this is actually a fantastic device. And we'll talk a little bit about, because it's for our dark energy search machine. And then, of course, we have, since many years, we perform experiments in the Bremen drop tower. And this Bremen drop tower is actually still the facility today, giving you the largest free fall time in a controlled environment. And you can approach in the front times as people dream in space. And actually, this is why we operate there. And finally, there are, of course, space experiments, rocket experiments, or it's fantastic. Currently, US scientists create PECs regularly in orbit on the space station, and we can actually operate this device. And yes, this is all where we can actually extend the free fall. So with the survey, I just outline a very long baseline atom interferometry device. You see here our logo. It's actually the symbol of Lower Saxony is a horse. And so we make a horse jumping through our atom interferometer. This is the spirit. Of course, it's not so crazy yet. The device, the goal is that we want to go below 1 nanometer per second squared in inaccuracy in gravity. So this would be the, from today's perspective, the ultimate gravity reference you can refer to. We think it is achievable, but of course we are not yet there. And also what is even an interesting sensitivity for accelerations at a single shot. And this actually makes a big difference to for example, Markasovich experiment, because he's measuring relative to species. And so he has a complete different, more or less, trajectory of scientific experiments. So, and why I mention this again, because, I mean, this is somehow, the idea is that we have absolute gravimetry, we have this with stability approach, sensitivity approaching superconducting gravimeters. We can do with it gradiometry and also curvature measurements all in one device. And now, of course, if you think there is now a network of superconducting gravimeter, wouldn't it be wonderful in all these stations, geodetic observatories worldwide, having such a device with all these capabilities? And on the other hand, for the people doing fundamental science, would it be not magnificent to have those to analyze what is maybe as unknown matter in the Earth? And so somehow you can again connect those to your research. So just saying that this is not so far what I'm telling you, I just want to present the facility and give you a flavor. I think it's one of the first times I really present those, but I thought maybe this, because we speak about these networks. So first, of course, our atomic sources will be both Einstein condensates, and we have actually quite nice results. One will be ytterbium, the other will be rubidium, but I focus on rubidium today. I present rubidium. Then we have a very nice baseline, what we call the free fall region. I explained to you, we want to increase the free fall time, so you have to increase the free fall distance, and this is 8 meters. This is here actually which is shielded magnetically. And then what makes us really special is we have an inertial reference, which is vibration isolated. Actually, we use gravitational wave technology to isolate our reference mirror with respect to whom we measure gravitational acceleration. And this allows us actually to really to win from the baseline and the long free fall time, because otherwise we would just fall into a sea of vibrations and would have no gain at all. So actually most devices today are not at the end of their performance simply because of vibrations. In principle, if you make it longer, you don't need to make it longer, except you really work hard on your inertial reference and your vibration isolation. And this is somehow. So just in a nutshell, we have create PTCs in the dipole trap with something like again 100,000, and getting something like again at a temperature of 110 nanokelvin, and we have quite nice laser cooling system as well, so that we can create a quite nice number of more than 10 to the 9 in very short times, actually. And so in a certain way, we even want to operate to realize the BC even in shorter time scales. So the atom chips are in our lab leading with respect to the dipole traps. So, but somehow the dipole trap team want to, of course, catch up. But somehow this is the atomic source. So it's and the next is that we have, of course, the long tube. And here you see actually the tube transported. This is the tube, the solenoid with the magnetic field. And actually, our PhD student who just left, finished, made an incredible job. So we more or less have somehow a nice vacuum, but we never explore this term, of course, in free fall, except we bounce the atoms. But we have also very nice magnetic field control. And here what it's given is bias in accelerations, and a nanometer per second squared would be a microgal. And so now you understand when we say we somehow work in parameter ranges, superconducting parameters work, then actually it's something like we are now more or less here. It's absolute scale. So we say this is a bias terms. And this means that we are very hopeful that actually we really can go below the microgal also in accurate measurements, but at least reach it, because so far the microgal inaccurate has not been obtained. We are about, I would say, 20 to 10 microgals. Microgal means nanometer per second squared in reproducibility or accuracy. And one of the key ingredients which will in future be important for us is actually the gravitational wave detector technique of an anti-spring system. This is an inverted spring where you can lower the resonance frequency, not just by increasing your pendulum length. And in this way, you get 320 millihertz of resonance frequency. And this gives you, if you look into with also active monitoring, we can hope again that our stability is getting into 10 to the minus 9 meters per second squared per square root hertz. So microgal or 1 nanometer per second squared per square root hertz. And this would be per shot. And now if you would also demonstrate integration capabilities, then you would see that again, this might be interesting in a network for also dark matter search. So this is just telling you that we, at the moment, so far, we see not a showstopper for reaching these goals, and so one day they might be useful for this. So I have been speaking so far. This slide shows you somehow complementing measurements of superconducting parameters in future with atom interferometers. The answer is, of course, dark energy part, and the force is due to this. And I have not been talking so much about it, but I mean, there is an idea, maybe there are better ideas, by Shenghui Zhou in NanU, that actually, Shenghui Zhou is a collaborator with Holger Müller, and Holger Müller was pioneering the ideas of Ed Heinz, said actually in chameleon field atoms are very nicely to detect those forces. And Shenghui Zhou had the idea that actually you could make stacks of those test masses, and then you get a periodic signal. And atom interferometers is a nice thing to rectify those signals, like a lock-in detector. And just letting the atoms travel through the stack of proof masses, and then flipping the interferometer with your light bulbs, such that you always end up the right signal and cancel the others. And so you could just detect the signal due to its periodicity. It's a nice idea, I think. But the problem is, of course, now in a very bold way, if you have gravity, it makes this, or it gets accelerated. So actually, to really get your sensitivity, you would have no gravity. And this brings me over to our microgravity experiments. And here they are. These are the experiments done in the drop tower and in the rocket. Here you see our BC device generation. All are operationable still. Some are already 15 years old, and they are shrinking and shrinking more and more. And the nice thing is that when we have done the rocket experiment is not dead. After it landed, actually we reuse them, and in this time we actually use them in the Einstein elevator. So I have not the time. I even don't know how much I'm in time, but you just stop me if you want that I stop. Anytime I can stop. We have performed a lot of experiments in the drop tower. I just should mention that this is a statement for its own, because you can at maximum do 2 experiments per day, and these experiments have to be shared with many other people. So actually, it has been very little experiments what we did in the drop tower. Nevertheless, we have been doing studying both ionization and microgravity. We have been studying the delta G collimation, and I will give you an update to what is just accepted now for PIL. For this, we also have been developing this high flux BEC source, which is serving as a gravimeter in another experiment, and which is in the rocket, was decisive to miniaturize it to fly it in the rocket. And this miniaturized system is then also for the first time, was the first scientific experiment which was flown in the catapult of Bremen. So you launch it up 100 meters, and so you get the nearly 9 seconds. And of course, we have been doing test of equivalence principle with 2 species. And actually, we have, I cannot speak about it because it's missing time. We have now 2 species atom trip interferometer, and we are preparing for next year rocket mission on 2 species. So we look into buoyancy and how actually the liquids are changing in absence of gravity. So here you see, again, just now a picture of our atomic source. I mentioned this paper here. It's always a pity with this. I cannot show you here on the bottom. You see, again, I have been talking about the high flux source, and here you see the drop tower on the very left side. And you have 2 modes. You can either drop it, or you can launch it with a catapult. And here you see our device, already quite compact. And here you see the heart of the device, an atom chip, which is loaded from a cold atomic beam. And here you see the multi-layer chip. And this gives us the capabilities which had been necessary to shrink the experiment to get the experiment rate up and still being reliable. Here you see it actually now in comparison with 2 PhD students. We can create PCs in all angles to gravity somehow in the way and studying it. And what we did most recently, I've been talking is about that we created this new record in lowering the expansion rate. And here I have been starting out with laser-cooled atoms on one of my previous slides. Here you see about, we just start at 2 nanokelvins comparing our system, and our current record is 38 picokelvin, and in 3D. And so now the question is, how do you achieve this? Because actually an atom chip is, creates you a more or less cylindrical trap. Now, the problem is that the cylindrical trap, the collimation is actually a very simple process. If you have a point source and atoms with different speeds start out from this point source, so you get a sorting out of atoms according to their velocity. The fastest atoms will at the end travel most far from the origin, and slowest will be closer. And now the simple thing is this sorting and this grouping actually allows you, if you switch on for a certain time an harmonic potential, you know that also with the distance, the energy you have to climb up is increasing in a harmonic potential. So you can actually precisely slow down all these grouped atoms according to their speed. And this is what we call delta K collimation. You can see it also as a lens. An optical lens is working the same. You have different effects along your optical beam and off axis, which you somehow then you have more or less a larger way to travel. And so you delay in a lens the light on the optical axis. So more or less, actually, you have precise the same ideas. A magnetic field is a magnetic lens for cold atoms, and an harmonic is actually a perfect lens, but not in 2-dimensional like for light, but in 3 dimensions. And an atom chip gives you a cylindrical lens. So you have one axis you can hardly control. But the nice thing is that easy you can create collective excitations, coherent collective excitations. And now you can have exactly the case which is shown here. Here, these arrows indicate just the expansion, which you would have if you would have no collective excitation, but just the proper phase of the collective excitation, in a case comparable, like a free expansion. But if you somehow then just apply the magnetic lens, you have the problems that you have in the weak axis only a weak refraction index, also a small refraction index for your magnetic lens. But when you more or less do your oscillation such that also the expansion is reduced compared to the transverse direction, you only need a less index of refraction in this direction. And this is how we achieve actually this way. And you see also here that this is the expansion in without the excitation, and this is the expansion with the excitation again here. So you see this difference, and this gives us, and here just very nice, the comparison between, so we go to 2 seconds, you see, nice to have a drop tower. We can really make so long time of flight measurements, and also our simulations, which actually can perfectly mimic what we see in our experiment. And here you see this expansion. I just wanted to show you what would happen if you would have not done this lens. You would shoot here through the graph. So and this is very important if you speak about space experiments, because now we can extend observations here. I give you time of flight. You can really think about that. The limit here is defined more or less by our detection limit. We can really extend it to 70 seconds. So the next what we will do is from a fraction of seconds, we can really observe species, 100,000 atoms expanding after 10-20 seconds. And this is what we will probe in our catapult in Bremen. So the catapult was actually have been the first scientific experiment with the catapult. And to show you again the nice flux of our BC machine, in these 9 seconds, we could, for the first time, create in a row 4 BCs and doing experiments with it. Actually, this is the picture which was on the title page of Progress of Physics. And it's very decisive because this was preparing the sounding rocket mission. And the sounding rocket mission was just lasting 6 minutes in space. You maybe heard about the discussion of the Kármán line with Galactic and the dispute with the space travel of the US companies. And this rocket was 6 minutes above the Kármán line. And but in 6 minutes, in old times, you had to make a BEC, you needed at least 1 minute. So you could have made 6 experiments. We have done 100 experiments because he had this high flux, and this is something. And this machine is now in the Einstein elevator. I mentioned that we have this magnificent elevator in Hanover at the high-tech. Here you see somehow a cute version. High-tech was founded by Wolfgang Erdmann, and also the Einstein elevator was initiated by him. You see this brand new institute, and in this tower, behind the walls, you have the Einstein elevator traveling, bringing experiments up and down. And not the text at least, but here I show you a link where you see actually the first microgravity created in this elevator. And this elevator is really specific. It has not the longest free fall time, but actually it's active, and you can do 300 flights per day. So you can really, I mean, compared to 2, it's a big progress, 2 orders of magnitude. And this really allows us to do better statistics and will accelerate our research there. And so we will look into this device. You see, it's a quite complicated system because it's an electromotor. And the electromotor drives up this gondola here in the middle. And this gondola can transport 1 ton. No, we don't need this mass, but just it's a beautiful microgravity environment. So if you have any microgravity environment in whatever domain, I can just recommend you. This is a facility, you can make use of it. So contact these people. You find it in the internet under high-tech. And but we also want to use it because we build in an apparatus for searching for dark matter in the elevator. And this atom trip should be not a problem. And I just here, we follow the ideas of Nan-Yun Zheng Zhou, where more or less we create a BEC on an atom trip. And we have here again our bright light pulses. And we let fall the system through the stack of proof masses. And we can do this on ground, of course, when it's accelerated, and we can do it in microgravity. And this, I think, will be for us a very interesting experience and see where we go. And actually, it's of general importance because we study a lot of mechanisms interesting for space. So this payload, as I mentioned, is stemming from a rocket launch. And this is what actually happened in 2017. And it was a great team of different universities. Here see also PhD students. And above you see the rocket engineers who were responsible for the rocket, and below the people for the BEC. It's a great cooperation with a lot of universities in. Also great theory support by University of Ulm, Wolfgang Schleich, as well as with the Darmstadt University, and people building on lasers from the Van Braun Institute and also University of Mainz and Hamburg. So we have a lot of people here. And actually what you have seen this picture for the Einstein elevator. Here, the system was assembled to a rocket. Here you see the red hull. This is actually these pieces, and here you see the atom chip apparatus and the according laser system, the electronics and batteries. Next, you see it is somehow squeezed, so it is quite tall, but reduced in diameter. But actually, we can do this now all much smaller. Again, I want to point out that most of the devices which are bulky are conventional techniques, not the atom optics. And here, just to highlight this device, of course, is again based on an atom chip, which you see somehow here positioned in the chamber, and basically you have as with this device. On the one hand, the cooling lasers and cold atomic beam filling the BEC. And then we had here, which is maybe important, for Bragg diffraction, 2 counterpropagating independent laser beams. I just want to mention that these independent laser beams means that we have not such a precise control on relative phase, which was for us also not important because we created just interferences to see about the spatial coherence. And in that sense, I want just to point this out because many people confuse spatial and temporal coherence. And here we had been really interested in how much it's actually similar like the famous Kettle experiments showing that, of course, you can define a BC about the expansion rate with respect to thermal background. But on the other hand, much more for us atom opticians, much more important is, of course, the spatial coherence. And this is combined from it. And this is what we have been looking into those. So this was about bringing the first experiment doing protein condensation in space. And this was somehow the flight plan. I just wanted to mention that the experiments we now do in the Einstein elevator can be extended to space because this technology is there. And so these are these 2 more or less papers when you are interested in what has been demonstrated so far as sources in space experiments. And in this, as I said, this was a single species interferometer. One of our drivers have been testing the Grill's principle eventually. And of course, then you need 2 species. And so it's not a surprise that in the next -2 mission will look into 2 quantum gases, potassium-41 and rubidium-87. And here we look actually also at the interferometry, but at first we look into the source properties again, because somehow it's like miscibility. You can have in gravity, you have layering. In microgravity, you have no layering. You have new structures, and it will be interesting. We can now have the pictures, of course, nice pictures of the layering on ground. And we are currently also making computer analysis, what we actually will get in space and how to look at it. So it's very exciting. And on the other hand, very important, because for simultaneous interferometry, of course, you have to understand those processes. And here below, you see just a nice picture of the, I said, I started with a picture with the sky above Sweden. And here you see actually the landscape of Sweden in wintertime. And here is the rocket launch pad, where the rocket starts, and CB is operated for the first mission. People have been waiting, have been working 3 months actually for the start, because in winter the weather conditions are that you nearly have such a nice weather as you see here below in the figure. And I think I should not finish these things with saying, and I already mentioned it, that of course, this is not the only experiment in space. We have currently experiments in space with doing proton condensates and also interferometry. And this is thanks to the Cold Atom Lab of NASA, which was recently launched 1 year, first time after our rocket mission. And it has actually exchanged already several times. And we are thinking about the next facility with extended capabilities. And I think it's also already published, but here you have the free accessible archive version of what we call BCAL, proton condensation and cold atom laboratory. And here actually you see CAL. So this is not BCAL, this is the cold atom laboratory, which is for us important resource for information, because of course, you know, if the first step is always the most difficult, the second is then already easier. And yeah, this brings me to the end of my talk. I have no idea how I'm in time. If I have been too long, my apologies. If I'm being too short, also my apologies. Then you can ask questions. I just wanted to give you, I started with the applications of light pulse interferometry and why we are working in this field. And I also somehow wanted to connect to your research, talking from gravity to gravitation and all what you maybe add in addition to gravitation, and the requirements with the motivation why we study especially light pulse interferometry with Bose-Einstein condensates, because of the better control. And then, of course, our activities in inertial sensing, which at a certain stage might be interesting to get information on dark matter and dark energy. And with this, I want to thank you all. I have thought I have even a final slide, but I lost it. But anyway, then I go back to this slide. And thank you for your attention. Thank you.
Thank you. So, have any questions? You can raise your hand or just turn on your microphone to ask. Okay, yes, Sergey.
Yeah, I have a question. You mentioned that there are two species of atoms which you use. One was rubidium. One is rubidium, and the other one was what was the other one?
Potassium.
Potassium. Thanks. Now, potassium is, if I remember correctly, there are quite strong interaction effects you can study using potassium atoms. So are you trying to avoid here in general the interactions between the atoms in the BEC, or is that also an interesting option for some of the research tasks?
I'm a physicist, so for me this is very exciting. Actually, we have to now nearly weekly meetings on what will be the experiments on the sounding rocket mission, because there we have only limited experiments. Of course, no, it was very interesting. And so we want to understand all the physics related to it, of course, and we have to, because in interferometry, we see that for interferometry, a lot of things are technically interesting, which for other people are fundamentally interesting. For me personally, of course, I'm a physicist. I like very much quantum liquids, but I'm not an expert, of course. I'm coming from atom optics. I'm fascinated about these things. And definitely there's, I consider that there is a lot of science to be done. Yes, I think this is one of the motivation for PICAL, and it is something what is very exciting. So regarding the drop-down experiments, we actually, the Quantum 2 experiment will be also upgraded to a two-species experiment. Then we hope that in a couple of years, we can do actually two-species experiments in the drop tower, in the catapult, to continue our rocket missions, and maybe PICAL is launched for 2027. I think we can do it even in orbit. Yes. Short answer, yes. We would be very happy if we could contribute a lot to quantum mixtures in space.
Thank you.
Okay, Dominique, go ahead, please.
Hi, thanks for an interesting talk. So I have several questions related to the interferometry. So I wonder, maybe I just missed this. What kind of states do you use? Do you use coherent states of light for interferometry, or some squeeze states, or?
Okay. So we use, precisely technically speaking, we use wave packets which are created by just releasing Bose-Einstein condensates out of the trap in free fall. and that's it. So strictly speaking, polyethylene condensate as such is only existing in the trap because it is the grounded of a trap. So if you switch off the trap, you don't have a polyethylene condensate anymore. But you have a released polyethylene condensate, and this is a quite unique feature, of course. And this is why we call it it's probably with polyethylene condensate. In very short, but you could speak, say it maybe more precisely, in the form with a released polyethylene condensate. Now, with respect, I'm just to these features. So the polyethylene condensate has a variety of features which I tried to explain, like the motional control you can have, and especially the extreme expansion rate. Also the high beam split efficiency, because the beam split efficiency deteriorates with a large expansion rate or velocities of the atoms, especially if we speak about symmetric two-photon processes like double Raman processes or double Bragg processes. They are very sensitive to the motional degrees or freedom of the atomic cloud you use. The other is, of course, when you have all this performance, when you have this high beam split efficiency, then, of course, you can also think of using entangled atoms. And yes, indeed, we cooperate with people in also using entangled and squeezed atoms, simply because often you would, you generally very, compared to light, you have a lower flux of atoms with respect to photons. So leasing would be even more interesting.
So I'm not sure if I understand this correctly. So the trap is released and the bosons and condensates then turns into light, and that's what creates this interferometry.
Can you repeat it? Because I'm not sure if I have catched all what you said.
Okay, so I'm not sure if I got it correctly. So you release the trap and that releases light.
No.
We see.
No. Again, so first the point is we switch off the trap for the atom, because there's our experiment a little bit special. Of course, in the drop tower, we also release the complete experiment. So it's not meant. When I say I release a BEC out of the trap, I mean I have a magnetic trap capturing the atoms. And I switch off the current of the trap, so the BEC is no longer trapped. And then this BEC is floating in free fall. Either it falls down on Earth or it is in orbit around the Earth. So it is just drifting. And then what we do is we apply at certain times light pulses. When shortly after the release, we apply a light pulse. Now, you can imagine, I don't know if you have do you have an atomic physics background? Because so you drive processes absorbing and emitting photons interacting with this light pulse. It's a Rabi process in principle. It's a Rabi cycle of spontaneous absorption and stimulated emission. And this Rabi cycle, you stop in a certain process, and 50% of the atoms are in their initial motional state. And with the 50% probability, the atoms are diffracted in a motional state with 2 additional photon recombinants. And this is what they make split. So the atomic wave packets are with 50% in the initial state, and with 50% they are more or less add 2 photon recoils. And these Rabi processes you can drive in a first in a certain way, at a second time, so that you reverse the momentum. Means that one, you just invert the processes somehow, and at the end, you do again what, a similar manipulation as in the first, where each of the atomic wave packets following different trajectories, at the point where they overlap, you drive again light pulses. So out of each of the trajectory, you get two new trajectories, but they overlap.
Mm-hmm. Okay.
Is this somehow, if there's something which maybe I should explain better, let me know, because
okay, yeah, I don't come from experimental background, so more like a theory, so it's difficult to consider all these factors for me.
Yeah, I mean, but it's similar, you know, it's somehow the process is here that I'm not sure. So you have two counter-propagating laser beams, light beams.
Mm-hmm.
And you have your atomic cloud. So now when you interact with these light beams, what's happening is that if I put now a momentum diagram, energy diagram, you have more or less somehow an excited electronic state and the ground electronic state. Let's say you are in the ground state. So what's happening is if you absorb a photon, you absorb the momentum of the photon, but you are slightly detuned. So I try just a bit. I make it maybe a little bit more precise that nobody is shouting. You're slightly detuned and you make this is laser one. And now the laser two makes somehow a de-excitation. So you are off detuned in energy. And so you end up in a state without spontaneous emission by absorption and stimulated emission. So you absorb a photon. Oops, what did I do? I understand this. I touched, yeah, now I'm back, sorry, I touched the screen. What you do is you kick the atom and then due to this process, you get a second kick because the first photon comes from here and the second comes from here, it's opposite, but as it is a stimulated process, you add up the recoil. And in this way, you get from your initial state to your final state, and the final state is in principle the initial state plus two photon recoils. Not sure if this is somehow explaining you what.
Yeah, it's much clearer now. Okay. I should probably read your papers, so that's very useful. Thanks.
Yeah, these are very old papers. You can look into in the beginning. It's a huge field now. I mean, I only explain you now the most simplistic. Of course, now these things are much more complicated because we do Bloch oscillations, we do symmetric beam splittings that actually we have processes going from zero momentum to minus 2h per k, plus 2h per k, what is symmetric Bragg scattering. So and then we further add momentum. So this thing what I have shown here is just the most basic process. In quantum computation, we would speak about qubits. In our case, we speak about still Rabi cycles. But okay. It's very basic.
Thank you.
What I showed you. Hope it was helpful.
Definitely, yes, it was.
Okay. Actually, I have one question. You mentioned that this device can measure detect dark matter and dark energy. It's through its gravitational interaction, right? It's gravity.
No, I did not say it. No.
No, it's not.
No, sorry.
Gravitational effect.
I'm sorry. No, the point is, let's go to this slide here. There's research now going on, and so Dimitri Butka is also active here. He is mentioned here, but also others working on detecting all kinds of signatures due to dark matter, dark energy. And one idea now, I think this paper, but other references in, and so they are much more detailed actually as this paper. The idea is there can be now different articles explaining you the dark matter. And I think all these searches I have been mentioning are for very light particles, so down to 1022 eV from extremely light particles, nothing what you have on high energy physics. And so there are different concepts that, for example, dark matter is bound inside of the Earth due to the gravitational potentials, and you can measure the existence by looking into additional accelerations which you see in your signal, your system, which actually would be a gravimeter is giving you. And so you could look, people search for rotating objects bound in the gravitational field of the Earth. The signal should give the parameter. I think it's too lengthy, but you can read it. It's statement is that you get accelerations in the order of 20 picometer per second squared or something. So fractions of a microgal. The other is that you have fields, and these fields couple lumps of domains, coupling actually non-gravitationally to your devices, either laser interferometers or superconducting gravimeters, and the domains are running across the Earth, and now different sensors would expect, because due to different couplings, change in the natural constants, more or less, this is hypothetical couplings, you get temporal signals, and only in a network you can get, maybe you can try to identify those signals. So it's a correlation measurement, but it's hypothetical. And so these are, I would say, non-gravitational interactions actually. And then this similar effect is when you look into near field gravitation, then you look for, you can look for deviations. And of course, deviations could also be a hint to chameleon fields, and they are somehow connected to dark energy or emerging from dark energy. And so you could exclude those. So I hope that this was somehow sorting better the statements I made.
So is there any bound already from the result that?
There are different bounds, yes. For the dark energy, Holger Müller said a lot of bounds. And I have a slide which maybe is also in this paper I mentioned. And also for the superconducting gravimeters, there's a bound. I can try to, so here the statement is the work expected by using this special periodic test masses in an atom interferometer for the exclusion. You see that these things are in 2017, and there have been maybe already again additional experimented quite moving fields. So actually the exclusion range maybe already by other methods been shrunken. And if you ask me about the one would have to look up in these papers for the let's see if I find this right quickly again. I'll show you the reference. Here we are. This should be some here. In this reference, there's a reference in for the different cases where people have been using superconducting gravimeters combined with laser interferometers or only superconducting networks. Yes, there have been set some limits, for example, to which sense the product of the mass and the Earth's the radius of this object fraction of the Earth radius can be, and the product was something I think like 10 to the minus 13 mass of the Earth times Earth radius. This quantity probably is now not very telling to anybody, but this is why I say I'm referred to the paper to see it. But there has been some limitations set, and maybe they are interesting for you.
Okay. Yes. Any other question? It's quite late already, so if there's no other question, let's thank the speaker again. Yes.
Yeah, so thank you.